Thank you, Danielle, and good afternoon to everyone. We will have a longer discussion time today than the last session, which was somewhat abbreviated, and I talked about the reasons for that last week. So we're going to talk about prospect risking, and the figure here is meant to be a structure map, deep coming up to a high point on a graben, down to the east fault, another low coming up to a high, another fault. And we'll call this the alpha prospect, and we'll call this the beta prospect. And so the question would be, should we drill either of these or only one? And if one, which one, alpha or beta? And if we think we should drill with two of them, which one should we drill first? So these are the types of questions that people in exploration deal with quite a bit. So the objective will introduce the types of considerations that are necessary if a prospect is ready to review the management. And the relevance is it will demonstrate some of the tasks that go into determining the size of the prize, how much oil or how much gas could be in the prospect, and risk, and determine the risk associated with that prospect. What's the chance that everything's going to work and we're going to have an economic amount of oil or gas? So we have at this stage in our analysis developed a geological framework. We're ready to do some data analysis and see if we have some prospects and see if they are viable, if they make sense in terms of drilling an exploration well. So we want to analyze prospect elements, and I've been talking about that since I think lesson 2. The source rocks, hydrocarbon migration paths, the reservoir, the trap, and the seal. We consider the most likely scenario or set of conditions, and then we might consider other cases so that we have a range of possibilities. And I'll talk more about this as the lecture proceeds. We want to assess the prospect. What sorts of volumes of hydrocarbons can we expect? And will it be oil only, or will it be gas only, or will there be oil with gas? And the volumes, we want to know how many barrels of oil or how many cubic feet of gas. And then we have to risk the prospect. What's our level of confidence that all the prospect elements work so that we have an economic success? So in terms of an outline, the first step we'll talk about is defining prospect elements, and S is for source, migration, reservoir, trap, seal. And so we have our geological framework, we're doing our data analysis, and we're defining one or more prospects. And then the next step is to do prospect assessment. How much volume does our potential trap hold? What type of hydrocarbon are we expecting, oil, gas, or both? Assess how much of that hydrocarbon we can recover up at the surface and therefore sell, and then assign a risk to the prospect. What's the chance that it's going to all work out? So to define the prospect elements, I believe this is from lecture 2, where I talked about the source rock, the hydrocarbon migration paths, and the combination of a reservoir rock in a trap situation with an overlying seal. So here's our example. Again, this is meant to be a structure map, deep up to shallow, so things would drain or flow by buoyancy up to the crest of the alpha structure. We have another deep going up to another high on the beta anticline, another down to the east fault where we have a deep portion going up to shallower depths. So our most likely scenario, what we think is most reasonable here, we are at 18 million years. The brown would be our basement rocks. The green layer is our source interval. The yellow layer is our hydrocarbon migration pathway plus our reservoir. And then the seal is the gray. And then the light tan is overburden, the sediments that were deposited and push the prospect down to depths where we can have hydrocarbon generation, migration, and entrapment. So the fault has not yet started at alpha or at beta. So let's move in geological times closer to, we model that the source rock is starting to generate oil at this depth. So in the deep to the west of alpha and nowhere else. And so we could have oil migration, and we could trap in this anticline at alpha that isn't yet cut by a fault. And if we spilled some, we might get a little bit of spilled oil into the beta anticline. Now we'll look at 10 million years ago. We now have a bigger area that's generating oil. We also have in this subbasin an area that we're generating oil. We can have oil migration into the alpha prospect and from this kitchen into the beta prospect. The fault now offsets the stratigraphy, and we're going to assume, at least for right now, that this fault is sealing so that we can trap oil against it. And the fault at beta is also sealing so we can trap oil against that. And then we look present day. Our oil window has gone to higher up on the structure. We also have a gas window where we're only generating gas. So we have gas and oil migrating into alpha, and we have a gas cap and an oil leg. We also have oil that's generated and migrating up into beta, and so we have only oil at the beta prospect. So this is our best guess as to what's happening. In map view, 18 million years ago, alpha may have looked something like this, an anticline with oil in it, beta anticline with less oil in it. 10 million years ago, the faults are in place. We have more oil generated and migrated in the alpha kitchen, getting up to the alpha anticline. We have some oil generated in the beta kitchen, reaching up to the beta anticline. And then present day, we think alpha has a gas cap and an oil leg, and beta only has oil, no gas cap. So we talked about this in a previous lecture. The explorationist task: identify prospects, capture those through lease sales, acquire additional seismic data, process the new data, interpret the data. And so we're down in this box that's in yellow. We need to assess the prospects. What's volume? What's the hydrocarbon type, oil or gas? We need to assess it. How much could there be? And then evaluate how risky the prospect is. And if we get favorable numbers, we present that to management, and maybe they decide to drill a wildcat well on our prospect. So we have to estimate trap volumes. And so here we have alpha and beta. Remembering our high school geometry, the volume of a cone is 1/3 pi r squared h, where r is the radius and h is the height. We could simplify the geometries here into half cones, a half cone for alpha and a half cone for beta. And so we would have a radius and a column height. And so this is a little diagram of a half cone. Again, 1/3 pi r squared h times a half, so it would be 1/6 pi r squared h. So if this was a cross section, let's say through alpha, we have the top of the reservoir, the base of the reservoir, the fluid contact where we go from oil into water. We can simplify that or approximate that by using half cones. So we could figure out what's the volume for a half cone for the top of the reservoir, and then we have to remove the volume associated with below the top of below the reservoir. And so if we get the volume for the larger cone, subtract the volume of the smaller cone, we would get the volume that's colored in yellow here that potentially would be the trap for oil and or gas. So exercise 10B, don't know how many of you have been doing the exercises, but we go through calculations both for alpha and beta. Line number 6 is the estimated ultimate recovery that is not yet risk. That'll be the next step. But alpha, we think if it only has oil, we'll have 320 million barrels, and beta is about half that size at 146 million barrels. So now we need to worry about risking those numbers of barrels. One thing we have to figure out or estimate or have a educated guess is the type of hydrocarbon. So typically we're early in our study, and it can be difficult to predict whether we're going to have oil in our traps or gas or a combination of the two. We can do things such as basin modeling and hydrocarbon system analysis to try to predict what is the most likely hydrocarbon fluid we're going to have. Are we in an area where we expect a lot of oil to be generated or only gas? And typically what we would do is we would consider a case if it is oil, and then a separate case, what if it's only gas? So for our most likely scenario, we have for alpha a gas leg, gas cap and an oil leg. Can we verify that this scenario is correct? To what level are the traps filled with oil and gas? Does oil go down to this depth, or is it shallower, or is it deeper? What would be the value in dollars or pounds or euros or yen if this scenario is correct? How much more or less hydrocarbon could there be? And how risky is the prospect? What's the chance that we are either totally correct or totally wrong? And sometimes, if we're fortunate, the seismic can give us some clues. So let's look at a seismic line across alpha. Here's the fault. The magenta is the top of the reservoir. The purple is the base of the reservoir. And if you notice, we have really red, and then moderate red, and then yellow. And where the moderate red turns into yellow, it almost looks like we have a horizontal termination of that red-yellow. That is evidence that we might have a fluid contact at that position. And then where it goes from the dark red into the lighter red, there might be another fluid contact at that position. If we have a prospect like this and we think we have two fluid contacts, it becomes pretty simple, because we're always going to have a gas cap over an oil leg, which will be over the water wet or brine wet sands. So the seismic in this case can tell me that perhaps this is the depth to which the gas cap extends, and this is the depth to which the oil leg extends. So now we have to assess the recoverable hydrocarbons. And so there's two ways we can do that assessment. One is deterministic. So we use one value for each of the input parameters, and I'll talk about those parameters in a minute. And we crunch the numbers and we come up with one final solution or one final number, maybe 200 million barrels of oil. The other type of analysis we can do is probabilistic. And in this case, we put in a range of values for each of the input parameters. And so we get a range of outcomes. And so it might be that we determine that our prospect has 200 million barrels plus or minus 50 million. So looking at alpha, we could come up with 4 n-member cases. There might be a gas cap and an oil leg, and if that seismic was interpreted correctly, that's we have some independent or geophysical evidence for this being the case. Maybe we say there's a 40% chance that this is what is happening at alpha. Maybe alpha only has gas in it, and we say maybe that's a 20% chance. Maybe alpha only has oil in it. We've assigned 30% to that possibility. And the fourth possibility is that we have a little bit of gas in the sand, maybe 10% gas, 90% water or brine. That's what we call low gas saturation. And we're estimating that there's a 10% chance that that might be the situation at alpha. So we can run deterministic assessments for these four cases, or we can do probabilistic analysis and come up with a range of possibilities. So this is what I showed you earlier. Alpha has 320 million barrels unrisked, and beta has 146 million barrels unrisked. And that unrisked means that that assumes that everything is going to work in terms of source reservoir, trap seal, migration, and our interpretations. I talked about the four scenarios: gas and oil is scenario 1, scenario 2 is gas only, scenario 3 is oil only, scenario 4 is low gas saturation. I can do a deterministic assessment, and for scenario 1, I come up with 112 million barrels of oil and 95 billion cubic feet of gas. We can turn this gas into equivalent value of oil. 6 billion cubic feet is equivalent in value to 1 million barrels of oil. And so I can come up with the oil equivalent of 121 million oil equivalent barrels. If it's only gas, there's no oil, 314 billion cubic feet. That turns into 52 million oil equivalent barrels. If it's oil only, then it's 192 million barrels. And if it's low gas saturation, there's nothing that is going to be economic and that we're going to recover. Now, we may decide that in this area, we have to have at least 100 million barrel oil equivalent in order for the economics to work out, i.e. for us to make some money. So this is greater than 100, so this is an economic possibility. This is below 100, so if it's gas only, we wouldn't be interested in drilling it, or if we drill it and find we only have gas, so we're going to find that we're going to have to abandon the area. If it's oil only, we're exceeding 100 million barrels, so that's okay. And if it's low gas saturation, we've drilled essentially a dry hole. So in our probabilistic assessment, we want to get a number with a range of possible outcomes. And so what we do, we input a range of values for each of the assessment parameters. Usually what we'll put in is what's the minimum value, what's the most likely value, and what's the maximum. So one of the assessment parameters is the area of the possible hydrocarbon field. And so in this case, the most likely we said was 20 square kilometers. It could be as small as 12 square kilometers. It could be as large as 27 square kilometers. And what we've used here is a normal distribution or a bell-shaped curve. We don't have to use the normal distribution. We can define what type of distribution that we want. Another parameter is thickness. Again, we'd have a most likely, a minimum and maximum. The net to gross, the porosity, the hydrocarbon saturation, the formation volume factor, that's how much expansion would we have in oil or gas from reservoir conditions as we bring it up to the surface. And then the recovery efficiency, what's the most likely, the minimum and maximum. So recovery efficiency most likely might be something like 25%, minimum might be 12%, and maximum might be 50%. We run with those parameters with their distributions. We might run 500 or 1,000 different simulations, and we come up with the red curve here, which is an exceedance probability. So there's 100% chance of finding 0 oil or gas or greater. The green line here is at 100 million barrels. So at 100 million barrels, there's about 72% chance of finding 100 or more, and so on and so on and so on. And so this is unrisked because we're saying that at zero, we're up at 100%. What we have to do is we have to discount these numbers based on how risky the prospect is. So if we have a 99% chance that everything is going to work, we're not going to discount it very much. But if we only have a 30% chance that everything is going to work, we're going to have to discount this quite a bit. We do have to assign risk. And so how confident are we? And so some people talk about a chance of success. And so maybe alpha has a 75% chance of success, 3 out of 4. Other people talk about risk. There's a 1 out of 4 chance that it won't work. So one of the keys to success in keeping a job is figuring out what your management likes to hear. And if your management likes to hear chance of success, then that's the number you report to them. So what we'll do is we'll think about how risky some of these different elements are. The source quality, the source maturation, hydrocarbon migration, reservoir presence, reservoir quality. Did we have biodegradation? What's the quality of the trap? What's the sealing capacity of the seal? And what's the chance that we would not have low gas saturation? And so we put a team of experts together to come up with the numbers as to what the risks are for these 9 elements. So for alpha, the biggest risk is that the fault does seal, because if the fault doesn't seal, we may not have anything in the trap. There's also a chance that the trap could be filled with low saturation gas. And so here we've assigned 1s to most of the parameters, but we said there's an 80% chance that the seal is adequate, or 20% chance that the seal is not adequate. And then we said it's 90% chance that it's not a low gas saturation anomaly that we're seeing, 10% chance that it is. If we multiply these 9 numbers together, we come up with 0.72, and so that's the chance of success. So now we can go back to that exceedance probability. 72% is my chance of success, and so this is where the red line intersects 0, not at 100, but at 72. And this portion of the curve that drops and then flattens out, that's the scenario where we only have gas in alpha. And then this portion, this plateau, is where we have a gas cap and an oil leg. And then from this point on is an oil-only case. And so we have a 72% chance that we're going to find some hydrocarbon. If 100 million barrel is the economic minimum, we have a 58% chance of exceeding that economic minimum. So 58 out of 100 times, we'd expect there to be enough hydrocarbons that we would make money. And there is, on the bright side, a 5% chance that we'll have 400 million barrels. And so this is the type of information management likes to see. Yes, tell us what you think the most likely case is, but how poor could it be and how great could it be? So that's my prepared statements. I'll bring this up in case we need this for discussions. We've talked about prospect risking, and on Thursday of this week, we'll talk about well seismic ties. And next week, Tuesday, we'll talk about seismic acquisition, and Thursday, we'll talk about seismic processing, both of these at extremely high levels, trying to cover these extensive topics in less than an hour. So I'll turn it over to Dr. Sumi and see if we have some questions from the audience.
All right. Well, thank you, Fred. I think that was a good assessment of what we can consider when looking at prospects. So yeah, I'll give it a minute so everyone can get their questions in. But I especially liked how you like that ranking system that you were just talking about, how you can look at each one of the factors and be able to decide, what your risk is for that particular prospect. So.
Right. I didn't mention it, but when we're assigning risk like that, usually what we get together is about maybe 10 people. And so we'll get 5 or 6 people that have been working the area in detail. And so that's local expertise. And then usually we get people that have a lot of global experience with source rocks, and somebody that's got global experience with reservoirs, and someone that's got global experience with traps. And so we try to combine people with local expertise with people that have seen a lot of examples. They've drilled a lot of examples that they have assessed, and then they can learn from past mistakes, if you will, what sort of things might be extra risky, what things might not be as risky as we initially thought.
That's interesting that you mentioned that. So is it mainly set up by there's the team of people who have been assigned to really looking into this particular prospect and have gathered all of the research and data, and then they present it to this group of people who have experience from all over the globe, and then they're ultimately the ones who are kind of voting and making a decision? Or how does that then decision-making process work?
Yeah, the team that has been working this particular set of blocks, maybe they have 4 or 5 leads that they're trying to get to drill ready status. They would review their work with maybe say 4 people with more of the global and long-term experience. And it isn't kind of like a lecture, they're really work sessions. So the local experts bring the global experts up the learning curve on their particular area. And then they'll sit in a meeting and talk about, okay, well, what do we think the likelihood that we have reservoir here? And what is the likelihood that we think it's going to be a quality reservoir that we'd be able to produce oil and gas out of? And so it's a combination of the local experts with the global experts who come up and say that the risk for the fault on alpha leaking or sealing, let's say, 80% likely that that's going to be a sealing fault.
Okay, great.
And a lot of it's done by consensus.
Okay. Okay, so it's not like who are the yays and the nays. it's more who, yeah, bringing it all together.
Yeah, usually they'll start out with a straw poll, and everyone will write down, I think there's a 80% chance the fault's going to seal, and somebody else has 95, and somebody else has 55. And so that'll be the point that initiate the discussion. You know, why did you think it's so high a likelihood that it seals? Why do you think it's so low? What can we look at to try to understand or quantify the risk a little better? And so the meeting may not be a 1 hour sitting everybody together. It may be a discovery meeting, and then they'll go and do some extra work, and then they'll come back and say, yeah, we think we've done some extra work on fault seal for alpha, and now we are all pretty much in consensus that 80% is the best number to run with.
Okay, great. Well, thank you for that clarification, Fred. I think that was really excellent. We didn't get any questions this time around. So with that, I will end the webinar. Thank you all for attending, and we'll see you. Oh, wait, one kind of did come in. Sorry, Fred. Sometimes this happens.
Right.
Slow connection. Dominic Naday asks, we saw different levels of the structural history showing the maturation, migration, and accumulation of oil and gas. But then we have the present day trapping style. So how do we model the initial structure at the start? And how are we sure of the initial structural model and the levels of where the kitchen and oil or gas was? Does that make sense?
Yes.
Okay.
we do a lot of computer modeling we come up with an interpretation of present-day conditions, and when we do that, we're somewhat defining what the history has been to get to present day. And so I don't remember the lesson number, but I talked about some of the basin modeling that we can do. I think when I talked about source rocks in lecture 7, I talked about how we try to model through time generation of oil from a source rock and gas from a source rock. When did a particular source interval enter the oil window? When did it enter the gas window? When did it enter the over-mature window? And we can do the same thing with the structure. If we have a series of either time structure maps or depth structure maps, we can try to strip off layer upon layer and decompact the intervals, make assumptions about paleo water depth or paleo elevation. And so we can model for different time snaps through geological time what we think the structural setting, structural configuration was. So whatever horizons we have mapped and their associated geological age, we can get modeled structural configuration for each of those horizon times, or horizon ages, I should say.
Great. Well, thank you for answering that last question coming in. And we had one more. Oh man, I'm not even gonna try with the name. Do we need to drill a well to get the ages of the formations?
No, we do not. Many times we'll have some information elsewhere in a basin or a sub-basin that will give us geological ages. And then if we correlate our horizons properly, we'll be pretty close. There's also a portion of seismic stratigraphy that deals with trying to make pre-drill age predictions. That's a topic that we don't cover in these series of lectures. There is several papers in AAPG Memoir 26 that the people interested in that particular topic could read and see what types of methods that we can do. My first, say, 15 years of work in industry was doing seismic stratigraphy in basins with very little well control. And one of the main difficulties I was given was trying to not only figure out where the major sequence boundaries were located and map them around, but also to assign an age to them in so many millions of years.
Great. Well, one more question that came in. Oh, so the question is like if they can ask a question from the last class, which sure is totally fine if you want to shoot that in really quickly. Wait a second for this person. Okay. This person had noticed that we mapped an unconformity without a well. I think that's the beginning of the question because it's more of a comment. Okay. Okay. How did we conclude on that particular horizon?
How did we
conclude on that particular horizon?
Okay.
Does that make sense? And the question, I guess, followed up too, is there anything to look out for when working with just seismic?
Okay.
Maybe two separate questions.
I have those. The the lecture on September 7th, when we talk about seismic sequences, I'll talk about how we use the termination of seismic reflectors, individual peaks or individual troughs, to indicate or give us evidence that we've had a major break in deposition. And so if I see several successive reflectors terminate, then that can tell me that I have a seismic sequence boundary. If it seems like I have a lot of dipping reflectors that had been cut off as if they had been eroded away, bulldozed away, then that would be seismic evidence that we have a major unconformity.
Great.
And dealing with seismic in general, seismic is much softer of a data set than well data, where we have rock samples or we have log signatures, we have a temperature, we have a pressure. Seismic is very open to interpretation. And so when we are doing seismic interpretation, there is always an element of how has the interpreter properly or improperly viewed the data and deduced where the fault is or where the horizon is, and how has he or she correlated a particular horizon throughout the survey area, crossing a number of faults where the horizon gets offset. So one of the things in some of the exercises, there's some questions about the confidence of the interpretation. And I always say that there are a couple of factors. One is, what's the seismic data quality? The better the quality, the more likely the interpretation is correct. The more noisy the data or poorly imaged faults or horizons are, the more likely we are to misinterpret them. The other thing that I look at is what experience level is the person that's doing the seismic interpretation. It's not given that a person with 20 years of seismic interpretation experience is always more correct than a person that's been doing it for 5. But normally, the more seismic interpretation a person does, the more basins they look at, the more different types of structure and stratigraphy they've analyzed and pulled their hair out over and sweated during the night over, the more likely it is that they won't be tricked by some of the pitfalls that can happen when you're doing the seismic interpretation. So we do have to recognize that seismic interpretation is a technical task, but there is also a lot of experience that a person can pull on when they're making a decision about how to properly map the faults and map the horizons and build the geological framework.
Great. Well, there's another question about, can we identify a para-unconformity from seismic, considering we do not expect any reflection termination?
If there are no reflection terminations, we would not have seismic evidence for the unconformity. If we have well information that tells us there's an unconformity, what we'll talk about Thursday is how we can take well and seismic data and merge them. And so if based on well data, we know where there's a major break in deposition, we can transfer that depth to the seismic section and figure out which particular peak or trough should we map in order to correlate that unconformity around.
Great. Well, that looks like everything. There's nothing else that's come through. Thank you so much, Fred, for spending the extra time answering a few additional questions. And yeah, that concludes our webinar. We will see you on Thursday at 2 p.m. Eastern time for well seismic ties. So see you then.
Hey, thank you everyone for tuning in.
Great, thanks. Bye.
Okay, bye-bye.